just looking at this structure, we have done a diode already as fabrication. How many masks do you think I will require to create this? Think of it. Of course, this is not what I am thinking, but just think of it. How many masks I require to create this structure? Okay, think of it. Our interest now is to find relationship between the drain current and the output voltage. This is an N-channel device, bulk is grounded, this is my gate, this is my source, this is my drain. Current through this I declare as IDS, and voltage across this is VDS. And the voltage I apply across the gate to source is VGS. And I am interested to know how IDS varies with VDS as I change VGS. If I had to do this, yesterday we already have said that if I put a VGS higher than threshold voltage, then I will see an inversion layer of electrons between source and drain. One guaranteed I did that this oxide was covering part of the source and drain, so that the inversion will occur throughout source and drain region. Let us say if this would have been here, this region probably would not have got inversion because there is no gate oxide there. So the mass requirement, just for that I said, I must cover source drain areas partly. Okay, so this is something which is mass related, but just to give an idea why covering. So we figure out that for those, if I apply plus VGS, which is greater than threshold voltage of this device, I am going to create an N channel between source and drain, and this N channel electron concentration will be decided by how much VGS I exceed over VT. Larger the VGS minus VT, larger is the number of electrons or concentration of electrons in the channel. However, yesterday I did not say it, but maybe worthwhile to show that if I, before it crosses VT or close to VT, the device was in depletion mode, and this diode, source bulk diode, both are reverse. This is reverse bias, and if this is positive, this is also reverse bias. So there will be essentially some depletion layer because of this, some depletion because of the VGS, and then this will be slightly larger depletion on this side. Why? Minus VDS will be applied across drain to bulk. Therefore, larger depletion near this. Now, this depletion layer is associated only with the gate. These two depletion layers are associated with the PN junctions sitting between source and the bulk and drain and the bulk. This is an assumption. So here is, before I derive this relationship which I said yesterday, my aim is to find IDS as a function of VDS, and if I find this relationship, then the next thing I would like to know about this, what will be its equivalent circuit. As we did equivalent circuit for a diode, we will be interested to know what equivalent circuit this will give. I just draw it for a few minutes, few days, we will prove that this is okay. If not okay, we will see how much it should be different. Right now, assume that this is sufficient. And this current source is EM times VGS. If this is my gate, this is my source, this is my drain, then VGS is applied here, and this is course we will derive this. This is just to show you what I need to do, why I am doing all this. My ultimate interest is to get this. Is that one clear? Because for me, when I solve a circuit, I should be able to replace my MOS transistor by something circuit equivalent of that. Because then only I can solve Kirchhoff laws. Therefore, I need to know how much is equivalent, what these capacitors are talking, what is this dependent current source. What is it called? Dependent current source, because dependent on the input signal. So it's a dependent current source. The output will be essentially this current multiplied by this impedance minus of that, and that is what we are going to get. So we want to know how much values one gets for CGD, CGS, RDS, CDS, and how much is this GM. Is that clear? This RDS is same as 1 upon GD. Yesterday I said GD, so it is the same thing. So this equivalent circuit is my, and then I want to know how much and how are they related. Now interesting thing which you all should know, this is called small signal equivalent circuit, AC equivalent. The terms which are interesting there is GM and RDS, of course these are capacity otherwise. Both these terms are AC values, RDS as well as GM. But to our great amazement, they are directly related to their DC equivalent values of IDS, VGS, VDS. So knowing the exact DC value of VDS, VGS and what current IDS I get, I will be able to derive the expressions or values of AC terms, GM and RDS. Once I know what does that mean, DC values I know means the biasing of MOSFET is once fixed, as we did for diodes and other terms that we did in the lab. As soon as I fix the bias, I am fixing GM and RDS. Is that clear? And once I know them, then I can solve this AC equivalent circuit with additional loads or additional hardware left side, left or right, and I will be able to solve full output input characteristics, which is what circuit people are interested in. Given an input, what is the output? That's what we are interested in. To do this, in between if the device occurs, I must be able to replace this by an equivalent circuit. Okay. Now this is what ultimately I am looking for, but to do this, since I must get this relation first, even to get this values, so I must first find how DC value of IDS is equal, is the function of DC value of VGS and DC value of VGS applied. So start with, let's say, a little bit of physics. If I exceed VGS just beyond an VT, now this is very interesting device which you are seeing here. Maybe I can expand this part here. This is my source, this is my drain. I'm not showing full of it, only this, and I am putting, okay, maybe right now you put that, okay, there is a VGS which is creating here. Now in the contra, maybe you can put outside so that it is visible correctly. Now, that when I exceed VGS in a capacitor, normal capacitor, please remember what's the difference between transistor and this is an oxide, this was the gate, and this was the lower plate of the capacitor. Now there is something very interesting happening. What is the voltage across this? We said VGS. So between the top terminal and the bottom terminal. Now in contrast to this, if you say an inversion layer exists here, and let's say I am having a VDS here with reference to source being grounded, then this is grounded. Then I figure out that since there is a current flowing in this, actually electrons will flow like this, but the actual current will flow the other way. Oh sorry, electrons will go this way, the actual current will go this way. I figure out that this is an N-channel device. So there are a number of electrons per cc in this channel, which is equivalent of some sigma. Now this means there is a voltage drop from this terminal to this terminal. So this I call Y is equal to 0, this I call Y is equal to L. y is my this direction, so I say y is equal to 0 to y is equal to L is the channel length. Width is which direction? The board, inside board, to that direction. So I figure out that at every point, this is say y-axis as I said, if you measure here, 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 everywhere there is a voltage which is not same. At source, how much is the voltage? 0. How much is at the drain? VDS. But in between 0 to L, that there is a voltage drop going from source to drain. This voltage variation we call Vy. Is that clear? So voltage in the channel is Vy. At every point, the voltage is exceeding from source to drain, ultimately it reaches VDS, starts with 0. Now this is different from a capacitor. If you see now this capacitor, this voltage is across all of it. But now at every point if you see, Vg minus the substrate which is channel now is different. Vg minus Vs everywhere is different. Is that which is the highest VGS minus VGS at the source end, because this will be 0. So this, but how much will be on this side? Vg minus Vd. Now what is the condition of inversion? I said the VGS must exceed, or Vg minus substrate voltage must exceed threshold. So it may happen that as long as this voltage minus this voltage, this exceeds threshold voltage, the inversion will set in here as well. But if it does not, the portion where it does not have that exceeding voltage, at that point inversion may not be exist. Is that point clear? So is it different from the capacitor? Saying as if there is a number of such capacitors stacked together. Every point there is a VGS different. So wherever it exceeds Vt, we say inversion will occur. If it doesn't, no inversion can occur. Now this is the difference between a capacitor and a MOS transistor. Is that clear? Because in a MOS transistor, the IDS is giving you a voltage drop at the substrate side. Even if substrate is grounded by me, upper layer is now connected from 0 to VDS. Channel has this voltage drop. Now this is something interesting. So larger this difference, larger is VGS minus VT, larger is the number of carriers inversion it can create. So where do you expect maximum number of electrons? Which side will have largest number of electron concentration? Source side. Which will have smaller numbers? Drain side. So the actual channel looks something like this. Is that correct? Assuming that VGS minus VDS is still larger than threshold, but VGS minus source voltage has the highest voltage difference, so the channel number of electrons in the channel will be maximum at the source end, or the thickness of the channel will be largest near the source voltage and will become smaller and smaller as you go towards drain side. This shape is called trapezoids. So the channel is not the, like in a MOS capacitor, what did we show? This much electrons. So we show X everywhere constant. This may not be true in the case of transistors. So the first thing you should remember, as if we have number of capacitors stacked one after the other, whose VGS are not same. Is that clear? And therefore, number of electrons they will invert will be different at different times. This is something interesting. And this will now tell us how to, therefore if I want to calculate even the current or the drops, I must take care of this voltage variation, because in a capacitor I solved it very easily saying same voltage. Now at every point I'll have to solve. So something I'll have to solve at y is equal to 0, something between this, y, and then maybe I'll sum it up or integrate it out to say, okay, totally how much IR drop I actually got. Is that clear? This is the difference between capacitor solutions. When this will become a capacitor, if I say both source and drain are grounded, no potential difference, no voltage drop, so then it will be like a simple capacitor. So tomorrow someone says, I want to make a MOS capacitor inside in a circuit somewhere, so what should I do it? I will not be given separate MOS capacitor. All that I do is drain source or ground, and that will act like a capacitor. What the advantage with this MOS capacitor is that as the voltage changes, the capacitor also changes by root law. The depletion layer is proportional to root of voltage. We have seen that VGS characteristics. So that also acts like what? Varactor. So a MOS capacitor is also a varactor. So most of the MOS technology people do not use junctions, but use MOS capacitor for their varactor requirements, variable capacitor. Let's look at since this is the figure I had drawn, maybe I should write down correctly because I should not forget. There are certain, yes. What is varactor? Capacitor which is function of voltage. If I plot C versus VGS for this, as VGS changes, capacitor changes. And this is depletion layer. Depletion layer is proportional to root of voltage. Okay. So it is like a PN junction with a step junction. It is similar if not exactly same. Okay. Let's come back to this. I just write down because I may derive without even telling you this, but let me write down the assumptions which I am making in derivations. This is very important in actual derivation. So whenever we make assumptions, what does that mean? That we are trying to simplify a situation which is not really simple. Because we want to solve analytically something, so we like to solve something with simpler assumptions, and if necessary in this course may not be, we will actually remove most of them, say okay, in reality this term will get changed, this term will get changed, but the first thing we'll say, if things are so ideal, nice, this is the VGS characteristics. In reality, it needs to be modified because these assumptions may not be valid in every case. Then how do we solve? Okay, we'll find where it is valid. Okay, at least in this region, this expression is valid. That is what we keep doing. Then the next region, we create another equivalent assumption. Say, okay, at least in this is also valid. That is how all models will be created, because otherwise you should always have to solve what? Numerical evaluations, because these will be nonlinear equations, second order, sometimes third order in some cases. In that case you cannot solve analytically such functions. Therefore you have to go on a system, use whatever methods you wish to use, first convert it into some algebraic equation, use Euler's laws, and finally solve functions you are looking for. But that can only be done by a system and cannot be done analytically very easily. There is a method of solving second order differential equation by Krylov and Bugliov. What is it? So kabhi maths karna hai to. Okay. The first assumption I make, gate is ideal. Gate is 205 में पढ़ाते होंगे यार आपको थोड़ा सा. Okay. Gate is ideal means I am right now assuming phi ms is 0, Qox is 0, and even interface states which is given by word DIT. No interface states, no fixed charges, and no phi ms. This is ideal MOS system. So to derive this, I will assume this ideal. Oh sorry, I didn't say it. The interface state density. That day I briefly said you, as I said, you will come back later. See, if this is your band, or maybe tomorrow N channel wala diya. What I said, because there is dangling bond between silicon and silicon dioxide, all silicon atoms, the topmost bonds are not filled, necessarily all of them. Number of states will be very high. As many atoms on the surface, those many bonds will be available. Some may get satisfied by oxygen, the others may not. That these is dangling electrons. These are called interface states. Essentially, they give states in the band gap. The lower portion is called donor state, upper portion is called acceptor state. This is also a partial assumption but valid enough in this cases. So first time when I apply gate voltage, the charge is exchanged not between semiconductor but between these states. They will fill it up or empty it depending on the charge I apply on the metal. So what will happen, that the semiconductor is getting screened, that is it doesn't get the voltage what I am charged equivalently, but first states filled up. So if the threshold has to be attained, you may find you may require additional this, first they will fill it up and then semiconductor bending may start to get you a threshold. So there is additional problem and this will keep on changing as the charge changes. So you can see there will be change in the capacitance as I increase the voltage, and that slope of the characteristics of CV essentially states it's a large interface state. As I say, some other day more detail or come to microelectronics course. Here we'll give much more. All that we do in our lifetime, last 50 years, is doing this MOS CV. Those who work on MOSFET only do MOS CV. Naam badal ke, karte ek hi. So let's look there, much more interesting part is look there. Right now assume interface states are zero. Then the second assumption I make, I already said there is an inversion electrons here, electrons are here. I am now assuming that there are no holes in this inversion layer. What does that mean? That means there is no gradient, there is no recombination there is no gradient set in. So which current can be neglected? The diffusion current. So the first assumption I make, that only drift current flows, which is not a very bad assumption in a semiconductor bar. Most of the current will be drift current unless there is NAX or NDX provided. Our assumption right now is along the length 0 to L, every layer is same. Assumption, fair enough, only drift current. As I say, if you come to fourth year again in micro, we will show you know there is some diffusion currents are coming in the very low channel devices now, and we are worried about those currents. As of now, we don't worry. We have already said in our semiconductor theory that the mobility of carriers is function of what? Which quantity varies with electric field and number of carriers. It's function of number of carriers itself, because larger the number they will scatter, therefore mobility will decrease. So mobility is a function of temperature, electric field and the number of carriers there. So our assumption is for a fixed temperature, mu is constant in channel. This is also an assumption. This may not be very true in many cases, because firstly this, when the device channel length reduces, EDS does. Please remember, this is very bad thing which is happening for our what we call scaling. When I say scale means what? I have initial channel length for say 5 microns in 18th. Now I am looking for nanometers. So what I am actually doing is dividing every time and say okay, next technology will have smaller thickness, smaller width. But the voltage is not getting scaled by the same value. 5 volts say 5 times the voltage gaya, channel length 100 times नीचे आ गया, dimensions 100 times नीचे आ गया, voltage 5 times से आया. So what has increased? Fields. That is our worry. So at smaller devices now, we are worried about stronger electric fields than what we thought in 80s. When I did this, I was very happy, nothing is going wrong. Such devices where nothing goes wrong is called long channel devices. Long channel device. So the theory is essentially for long channel device. When we come to short channel devices, we keep adding, oh, ye ho raha hai, ye term jaate, ye ho raha hai, ye dalte. That's what we keep doing. But right now assume it's a long channel device, mu is constant, which is, as I say, is an assumption good enough for a long channel device. Fourth assumption I make is, that's what I say, this is essentially related to both of them, but discretely written on it. Doping in channel is uniform. No gradient, therefore no drift current. This is again an assumption that the carrier concentration all levels is uniform, everywhere. We are thinking this will not happen, so we may take care how much it varies and what it may add. The fifth point I say, reverse leakage current. There are two reverse leakage currents. Things up. There are two reverse leakage currents here, or other two leakage currents here. Which are the two I am talking? This, yeah, first is the gate oxide may leak, so it's a gate leakage. Maybe not very large because the thickness of gate will be here is very thick, nothing much will come. What is the other leakage? Diodes, reverse bias diodes. So the two leakage currents are present, but our assumption right now, these currents are very small or negligible, tending to zero in our evaluation. And the most important assumption, which should have been number one in fact, but maybe, our most important assumption in deriving this is this. The electric field along this direction, plus or minus whichever is, Ex, or X only, we need not put like this, Ex, the electric field in the vertical direction, which is the field effect field, okay. This Ex is very large compared to Ey. What is Ey in this case? Dy by whatever X or Y, or dV by dy. So along this, whatever is the electric field, what is the maximum electric field? Radius by length, that's the maximum Ey you will get. This field is much smaller compared to Ex. What does that mean? That this field does not change anything in the channel. All that channel electrons can change it only because of this field. Gate is controlling the number of electrons in the channel, no one else. In reality, this may not happen correctly because as you shrink, Ey will become closer to Ex, and it also will influence to some extent the carriers in the channel. But our assumption in ideal model is Ey is very small, Ex is very large, so gate controls whatever carriers you can use for currents. This is our assumption. This assumption is most important in derivation, is called gradual channel approximation. So having told, okay, these are the possible, I repeat, this is most important. I say gate controls the inversion and nothing else. Okay, this essentially means Ex is much larger than Ey. The carrier concentration in channel is only decided by the gate bias, nothing else. Okay, so let's solve this problem now. Can I remove the left part so that we can start doing some maths on that side? Let's take so you have an inversion layer which is trapezoidal right now shown to you, and we have an element of dy at y. At any position on the channel length, there is a point y at which there is an element of channel I am taking which has a thickness of dy. Is that correct? dy. Let us assume, since I already said only drift current is flowing, this is acting like a resistor. Is that correct? If only drift current flows means J is sigma E, that means only a resistor is between source and drain. The value of resistance is decided by the gate voltage, but once that is fixed, the R is fixed by. So this element, let's say, has a value of resistance which is dr. So let's say dy is the element at y in the channel, and dr is the resistance associated. Now one interesting feature you should see, if the electrons, this is positive voltage, this is negative voltage or ground, so electrons can only go from source to drain. Therefore, from wherever the electrons start, that is called the name source. It sources electrons. Is that clear? And wherever they are received or comes down, that's called drain. So electrons go from source to drain. But one thing you must appreciate, that since if these regions are similar, identical, if I change the polarity, the other side will be called source, this side will be called drain. It is immaterial which one. Whichever gets the bias, correspondingly source drain will be actually defined. But in real circuits these days or real devices, source drains are not same. They are differently made, therefore these are not interchangeable as shown here. They are called asymmetric source drains, in which source is source and drain is drain. So you cannot change the device like this. If you change, it will be something else. So that's different, so just for the paper. So if IDS is the current flowing in this, in a circuit or in an area, there cannot be more than one current. So the current from source to drain is only one current, which is IDS. From here to here, only one current can flow, which is, and no diffusion current, I already said, only drift current. Net current in a circuit is always constant. So if IDS is the current in the channel, then dVy, voltage at point V, point Vy is IDS drop at that point must be the dV change in the voltage there. Okay. ऐसा क्यों करना चाहते हैं? Because channel length is varying from 0 to L, so is the voltage varying from, Vy is varying from 0 to VDS. So I want to take an element, solve for it and integrate it out. Now, how much is the dr? dr is rho L by A or L by sigma A. Okay, you know resistance can be given as rho L by A or L by sigma A. I want to know how much is sigma here, how much is A here, how much is L here. For the this small element, how much is the length of this element? dy, is that correct? So dr, so maybe I'll rub this, dr is length is dy divided by area. Now area is something which is catchy right now. Now one can see from here that as you move away from the surface or interface, the control of gate will be smaller, because most of the electrons will first come at the interface and then they will start having. So there is a gradient, not along this axis, but along the vertical axis. The length of, the width of this channel, or what we call the thickness of this channel at this point is called xc. So along x direction at that dy point, let's say x is the channel length. Is that correct? So what is the area then for this element? X into W, because there will be, this W will be appearing. So area is Xc into W, is that clear? Into sigma, because sigma is the conductivity. Now this sigma is slightly varying. The reason is, as we have just now said, along this n is as if varying. So there is a profile in this element which you are looking, Nx. What is conductivity? Maybe can we rub this side now? If you have noted down this, The next relationship we want to know is the sigma. Sigma is Q mu n in our case into n, whatever inversion charge. But this is, so I say okay, I'll get sigma average, which is 1 upon xc 0 to xc q mu n nx. यार मैथमेटिक्स का बहुत स्ट्रेट फॉरवर्ड मेथड है कि यूनिफॉर्म, एटलीस्ट देयर इज अ यूनिवर्सल ग्रेडियंट क्रिएटेड एंड वी से ओके if I integrate q mu n x dx from 0 to xc, in this element I know how much is sigma average. Is that clear? Is that clear, Gautam? Along this element which is shown here, larger electrons, smaller electrons. So conductivity of this is the average conductivity along this direction. So I just integrate it from 0 to xc and divide by xc, because then average is by in that distance. So integral 0 to xc q mu n x divided by xc is the average value. Now this is very interesting. Sigma average into xc is 0 to xc. If I take q mu n outside, now what is this? Can you tell me? What is this that dx I am looking for this part? What is the part? What is this part in the whole channel? This is the inversion charge. Please remember, nx dx means how much? Density. Nx dx is density now, charge, and if I put q inside this, maybe I can put q here, this is nothing but inversion charge at y. Is that correct? This is inversion charge density at y. Is that clear, Pawan? Nx dx into q, if I integrate over this, per cc into distance is per centimeter square, q if I multiply it to charge. So this essentially is mu n y at y, because we are doing right now only at point y. So dr, I put it here as sigma average, and then what do I substitute here? Dy upon this value I can replace by mu n into q n y. Of course, there is a sign which will be opposite because it's the electron charge, but right now assume positive, magnitude of that. So put plus value. Otherwise, you should always do correct signs or put something like this, magnitude. Now, please remember, the inversion charge I can always calculate from where? The capacitor theory we have already done. At this element there is a MOS capacitor going on, and I know inversion charge is related to voltages. Which way? If I apply VGS, part of that will go to Vox, part will go to the semiconductor. No other charges are there, so whatever I put there will come to the semiconductor, opposite way. Now from there, from the capacitor theory, we have already derived expression for inversion charge. Just before inversion, strong inversion, what is the charge we have discussed? The depletion charge. But when you exceed Vt, then there is a depletion charge plus additional inversion charge which is coming, and I am interested in that additional charge. So I must get total charge in the semiconductor and subtract so-called depletion charge, and then whatever I am getting is the additional semiconductor charge which in inversion I am going to get. This fact what I want to use. So I now say, if I can get this term, then before we go ahead, now I say, if I go from here to here, what is the voltage going to change? I am now using this, I am going back here. dVy is equal to IDS multiplied by dy divided by mu n q n y. Yes? Oh, sorry. You are very good. Oh sorry, उसमें भी W रहेगा. That W is sitting there. Now, how much is length varying, dy varying? 0 to L. And by that time, how much dy varies? 0 to VDS. So I said, okay, IDS dy is equal to W mu n. These are of course constant. Q n y dV by 0 to उसने ये इस टर्म को इधर लिख दिया और उसको इंटीग्रेट कहाँ से कहाँ, सॉरी इसको भी करना, 0 to y varies from 0 to L, voltage varies from 0 to VDS. If I now, please remember, this is constant, so it's not a function of y, because we say in a circuit only one current can flow. So IDS is universal from 0 to L. However, two things also should be told. Of course, so I must get some relationship with Q. Q is equal to CV. Do you get this relation? तो इस Q को किसी तरह से कैपेसिटेंस और वोल्टेज से मैंने रख दिया, तो फिर ये वोल्टेज का इंटीग्रेशन कर सकते हैं. Is that clear? And if I do that, this capacitance term may come out, okay, and only voltage term will appear here. And what will appear here? IDS into length, integral dy is y and length is this, is equal to W mu n integral 0 to VDS. Now this I had to find out, and that's what I'm going to do. Or IDS, and now here is that term start appearing, mu n W by L. Before we solve, can you now start looking, this is a VDS term, but Qn is function of what? Inversion charge is decided by the vertical field, that is VGS. So now did you get? IDS is not only function of VDS, but also function of VGS. You are looking for a relationship between IDS, VDS and VGS. This equation has now, if I substitute properly Q, then I see I have a relationship between IDS, VGS and VDS in one go. Is that clear? Q and Y term will give me VGS dependent, and integral from this to this voltage for length will give me VDS dependent. Is that clear? So I have a current which is related to VGS, and I have a current which is also related to VDS, or the relative ratios or relative values of the two. That will decide my IDS. Is that point clear? Another issue to be before we actually solve this is W by L. What does that mean? Even if I, by the way, the word I just few minutes ago said scaling. What does scaling mean? The dimension be scaled by some number. Let's say I have 1 micron technology, I say okay, I want half a micron, so put everything by 50%. Channel length will also reduce, channel width also be reduced. So W by L doesn't change. Is that correct? If I scale, W by L doesn't change. Is that factor clear to you? Individually length may change, width may change, but the ratio does not change. Current is therefore not proportional to the technology directly, but it is proportional to the ratio of W by L I am going to use. Is that clear? This is most important in design, that it's the ratio which is giving me current and not the values of individual. Is that clear? So L may be very small, so as W can be reduced. So ratio still can be maintained of what value I want, 4, 8, 16, 32. Generally these will be the values. Why do you say I chose this number? W by L will be typically 4, 8, 16, 32, 64. Why? What's the numbers are? Binaries. Okay, we are 2 to the power binaries. So 264 is any number. Generally, this is essential because when I make designs on a computer, the lengths are much easier to double every time. Because if I make a unit, I just double it. So double it, double it. So all the numbers will always go 2, 4, 8, 16, 32 points. This is just for those who will become designers later. So one word I have spoken that W by L is normally decides the current. If everything is same, VGS, VDS is same, this is constant. W by L will therefore increase the IDS. The other term which is seen here before I integrate is this mu n. In this integral, I quietly took this mu outside. But in reality I said you, mu n is also a function of electric field, carriers, all that I said, but that's not the worry I am really having. I have more worries in mu n than what I said earlier. So mu n, this inversion layer I have shown you very thick, but typically it will be 1000 angstroms, okay, 0.1 micron or so, thicker portion. In this 0.1 micron thick inversion layer, electrons which are closer to the interface, this is silicon dioxide, this is silicon, is that correct? Two different materials where when they come together, they have some kind of 2 or 3 kinds of forces. One is van der Waals forces, which is because the atoms are separated differently, which is binder. The other force which is acting is called surface states, which I said. These acts like traps. Any state is acting like a trap. So the actual carriers which with moving with such a mobility actually never move with that much mobility. It's called surface scattering. So the word is surface scattering. The mobility at the inversion channel. What is the bulk mobility for electrons in silicon? What is the number I gave you? 1350. Of course that can be vary from book to book, but typically assumed value is this. But if I say mu n surface or inversion layer, the best of mobilities people have got best, okay, is 800. Because of the surface scattering. And in most cases, you may get 600 to 650. Most cases, the mobilities which you get in the inversion channel is 600 to 650. If you do fantastic processing, what does that mean? The interface states are minimized by good processing, then it may rise to 800. But at no time it will go to the bulk value. This fact is also important. That means, since this is not as high as 1300, the current which MOS transistor is going to give will not be similar like bipolars, because part of the mobility is killed right here. Is that correct? So this is another issue why MOS device does not give equivalent currents as if in bipolars, where most of the current is transport like this, by mu 1350. Here it is half of that. Is that correct? For the same everything device, the current will be there for half here, because mu is generally half of bulk value. This is another issue why MOS transistors are low power, because this is smallest current. However, they should perform the same functions. If they do, then I damn care whether it is low current or high current. If logically I perform or amplification I do properly with lower power, then I have achieved much more. Is that correct? That's my ultimate aim. So MOS transistor some way is helping me, but it hits me differently. As soon as you say mobility is lower or currents are lower for the same values, the current charging a capacitor will also charge that capacitor or discharge it. This means the speed of the circuit will be rise. So the advantage of power reduction is not so great. To increase that, what should I do? I should increase W by L. Yes, 2 minutes. I should increase larger W by L transistors, so that what will happen? It will provide larger current. But if I do that, what things I extend? If W by L is larger, this is the area of the transistor increases, and capacitance is proportional to area, so the capacitance increases. तो एक तरफ आपने करंट बढ़ाया, दूसरे तरफ कैपेसिटर भी बढ़ गया, इसको चार्ज. इसका एक जोक ऐसा है कि ये एक इन्वर्टर डिवाइस है, इसका इनपुट कैपेसिटेंस जो है वो सियोक्स रिलेटेड है, एरिया रिलेटेड है। इसको यदि आगे कैपेसिटर को चार्ज डिस्चार्ज फास्टर करना है तो इसका साइज बढ़ाएंगे, इसका साइज बढ़ाएंगे तो ये बढ़ जाएगा W/L, इसके बढ़े, ये पहला वाला कैपेसिटर बढ़े, उसको चार्ज करना है तो उसके पीछे वाले को बड़ा करना पड़ेगा, तो उसका इनपुट बढ़ जाएगा। फिर कैसे करें? करवा के दिखा, इसको बढ़ाने के लिए बढ़ाया साइज, पीछे वाला बढ़ गया, उसको कौन ड्राइव करेगा, और उसको बड़ा लाया, उसको बड़ा लाया तो उसका इनपुट बढ़ गया। कैसे करते हैं सर्किट में, that I still live with it. Okay. Otherwise it seems that I cannot speed up any time. ना, इधर बढ़ाएंगे तो पीछे से मार खा जाऊंगा। So that's the way all designers look. यार इधर गया तो उधर जाते हैं, उधर कैसे बचाएं? That's all that expertise is all about in design. How to get rid of these issues is very relevant. So we'll come back to it next time about that is